We've all experienced it. You reach for a fresh cup of coffee, and before you even consciously register the heat, your hand instinctively pulls back. Our bodies are deeply sensitive to hot and cold environments. Because of those intense physical reactions, we tend to treat hot and cold as absolute physical facts. But if we actually test our biological senses, they turn out to be highly unreliable judges of reality. Look at this textbook experiment. Immerse one hand in cold water, the other in warm. Then plunge both into room temperature water. The cold hand feels warm, while the warm hand insists the exact same water is surprisingly cold. Your hands are touching the exact same liquid, but giving you opposite answers. That happens because human touch doesn't measure objective thermal reality. Our nervous system only measures the difference between what we were feeling a moment ago and what we are feeling right now. Look at these particles to see what is actually happening. Temperature is entirely dictated by the physical movement of molecules. When particles vibrate slowly, a substance is cold. When they vibrate rapidly and collide, the substance is hot. It helps to separate temperature from heat. Heat is the actual energy transferring from one object to another, like the fast particles bumping into the slow ones. Temperature is just the measurement of how intense that energy is at a specific moment. To track that intensity accurately, we rely on the thermometer. Instead of using human skin, these devices use materials like mercury or alcohol that react predictably to thermal energy. The liquid expands when it gets hot and contracts when it cools down. This textbook page illustrates a vital concept, the least count. The least count is the absolute smallest change in temperature a specific thermometer is capable of measuring, marked by tiny millimeter lines. By observing exactly how thermal energy forces a liquid to expand inside a glass tube, we bypass our subjective feelings entirely. We let physical matter measure the invisible world for us. Thermal energy spans an enormous range, from solid ice to boiling liquid. Because of that extreme variance, no single instrument can measure every environment. We have to design specific tools for specific domains. This vintage clinical thermometer is built with a highly restricted range. It tracks the narrow window of human body temperatures. As this diagram shows, the clinical design features a narrow constriction, or kink, above the bulb. This physically prevents liquid from rushing back down, holding the reading steady for a doctor. Look at figure 7.6 to see how that differs from a laboratory thermometer. Built without that kink, they track massive temperature fluctuations continuously, read while perfectly upright and fully submerged. If you try to swap their jobs, both fail. A lab thermometer drops its reading the exact second you pull it out from a patient's mouth. And if you drop a clinical thermometer into a beaker of boiling water, the extreme heat expansion will shatter the delicate glass. Here on the right, we see how modern engineering solves different problems entirely. Non-contact infrared devices skip the physical transfer of energy, using sensors to detect the thermal radiation a body is emitting from a distance. Obtaining objective data depends on matching the physical mechanics of the instrument precisely to the environment and the specific range of energy being measured. Gathering accurate data is only the first step. For that information to be useful to anyone else, we need a standardized numerical language to communicate it. The Celsius scale provides a highly logical framework for this. It is anchored directly to the physical behavior of water, marking the freezing point at exactly 0 degrees and the boiling point at 100 degrees. The Fahrenheit scale remains deeply embedded in the United States, used almost exclusively to track regional weather forecasts, cooking temperatures, and daily life. For advanced physics, scientists rely on the Kelvin scale. Named after its creator, Lord Kelvin, this is an absolute scale. It starts at absolute 0, the theoretical temperature where all molecular movement completely stops. Together, these three scales act as translation layers. They convert the raw physical reactions happening inside a glass tube into mathematical data the whole world can understand. Standardized measurement is essential when we push into extreme environments. Tracking minute shifts in the cold helps researchers prepare for and survive in the harshest climates on Earth, like the freezing plains of Antarctica. Instruments like this maximum and minimum thermometer are built specifically for that environmental tracking. The U-shaped tube automatically records the highest and lowest points of a day's weather, capturing data without requiring constant human observation. Our biological senses are perfect for letting us experience the immediate world around us, but to truly understand that world, survive its extremes, and push the boundaries of science, we have to recognize our physical limits and trust the tools we built to reveal what is actually real.